Hi, I'm Mrs. Bauer. This is
Louisa,
and this is
John Lucas.
John Lucas, and we are going to introduce forces to you. So up until now, yes, we were talking about motion. Another term for motion is kinematics, and we are kinematics, yes. And then we're going to start talking about forces. And another term for forces is dynamics.
Dynamics.
Yes, and forces cause a change in motion. That's how they're related, yes. Okay, so let's talk about the types of forces. Forces could be broken up into two groups. They could be contact forces right here, or non-contact forces.
That's not good.
When that's not, no, it's okay. So contact forces, there's two types of contact forces. There's a push and a pull.
That's not good.
That's not good?
Because if you pull really hard on a stuffed toy, it would break.
Yeah, you don't pull really. You have to be gentle with your toys, huh?
But if you pull really like this, if you pull like that, nothing's gonna break.
That's good.
Okay. But if you hit someone really hard, it's gonna hurt, right?
Yeah, you don't hit people.
But if you hit.
Okay, let's move on.
If you hit very slowly, if you hit like this, then that's okay, right?
Yes, that's okay. Okay, so the one non-contact force that we have access to all the time is our gravitational force, and we denote that with a W. Why would we use W for gravitation?
Weight.
Yes, the gravitational force is called the weight. Was that good? All right. Electromagnetic force could be broken up into electric and magnetic, and we use M for magnetic just for right now. There's also the nuclear force that keeps the protons and the neutrons together in the nucleus of an atom. It's good to know that it's there. It completes our force diagram, but this is the end of that conversation of nuclear force for this course. A pull is we call pulls tensions. Usually we're pulling objects with strings. Here, have some more.
Oh, that's good.
No? Yes. And pushes, there's two types of pushes. Oh, tension we denote with the letter T. There's two types of pushes. There's a push, any type of regular push is called a normal push. Normal is actually a math term, and it means perpendicular. So normal means perpendicular, and so we call it a normal force. Okay, guys, let's look over here. My students are watching you. Okay, yeah, okay. And it just means perpendicular. The other type of push, which you may not have thought of as a push, is called a frictional force. And we denote that with a little f, a lowercase f. So, the way that we denote forces when we have to write our forces is we'll write what type of force it is. So let's say it's a frictional force, so we'll denote what type of force it is. And then we write two subscripts, by and on, with a comma in between. By is what is causing the force, and on is what the force is acting on. Okay. Louisa, here, turn around. You want to help me with something?
Yes.
Okay. Here. Hold this. You don't want this. It's okay. Okay, so let's do an example. So let's say we have a book on a table. So Mommy's going to draw a book on a table, okay?
Okay.
Oops, down here. Let's see. That's our table. All right? And then I'm going to draw a book. Oh man, this is not my best drawing, but that's okay. Does that look like a book on a table? Yeah?
But it's a pretty table.
Oh, thank you. Okay.
It's like some art did on it.
Okay, yes. Okay, so let's see.
Looks like someone painted
We're going to
it.
draw things called free body diagrams, or FBD for
What?
short.
Wait, I said it. I want some more orange.
Hang on, so I'll get it for you in a second.
Okay.
So, free body diagrams, we
Wait,
denote
it's getting light.
whatever object we're talking about with a dot.
Is it getting light?
And then
Why?
we draw all the forces acting out. So,
Why
Louisa, what's pulling the book down? What's keeping the book on the table? You say gravity.
Gravity.
Gravity. And that gravitational force is called the
Weight.
weight. Very good. And weight starts with the letter what?
W.
W. Very good. So weight starts with the letter W. Now, what's causing the weight? We are here on Earth, so it's the Earth, and it's acting on the book. Okay, now, let go. Now, if it was, okay, so if it was just, Louisa, please, if it was just the book on the table, then we would have, welcome to my world.
No, it's getting light.
If it was just the gravity pulling on the book would be falling. But something is holding the book steady, and it's the table.
I was gonna say that.
Oh, good job. So the table is pushing, and it's not friction, so it's normal. It's pushing the book up by the table on the book. Okay, we're going to get a lot more practice with free body diagrams in class. This is just an introduction. Okay, so just a little bit of background. Aristotle was the first physicist. Look at this guy, Louisa. Aristotle was the first physicist. He was born in 384 BC. And he was the first one to think about like what's making things work. And he had a lot of ideas, and unfortunately a lot of them turned out to be not exactly correct. But that's okay. So Aristotle's idea was that there's a resting place for everything, and heavy things would have a resting place on the ground, like books or rocks, people, and light things like smoke would have their resting place up in the sky. And so everything was looking to achieve its natural resting place. So left alone, things would go to the resting place and just stay there. Now, it wasn't, and no one really questioned this because that's kind of what they observed, what they saw happen in their lives. No one questioned this till Galileo in 1500. It wasn't until the 1500s that someone else came along and really try to think about and challenge Aristotle's ideas. So Galileo said he did this thought experiment. He had a ball on a ramp. And so the ball is rolling down the ramp, and the ball would be speeding up or accelerating down the ramp. Now, if the ramp was a little more shallow, the ball, oh, great job. The ball would speed up, still going down the ramp, but not speed up quite as much. And if the ramp was a little bit more shallow, it would speed up not quite as much. And if it was shallow the other way, not quite as much. Now, what would the ball do if the ramp was perfectly level? What do you think? Would it speed up?
Yes.
No. No, it won't. The ball wouldn't speed up or slow down. If it was frictionless, the ball would have no acceleration. Now, I know we haven't talked about acceleration quite yet, but acceleration just means speeding up and slowing down. So if things aren't speeding up and slowing down, it has no acceleration. So what Galileo said was, an object at rest stays at rest, and an object in motion...
Give something to Daddy now?
No, hang on. It stays in motion at a constant speed in a straight line unless acted upon by an outside force. What Galileo, he actually didn't have in a straight line. It wasn't until Newton added in a straight line. So, Sir Isaac Newton was born the year that Galileo died. Newton took Galileo's ideas and he expanded and refined them a little bit. And we have Newton's 3 laws that we are concerned with.
Mama, I got a balloon back for Daddy.
Okay. So his first law, Newton's first law means no net force, total force, net means total, means no acceleration. No acceleration means constant velocity. So what Newton said is an object at rest stays at rest, and an object in motion stays in motion at a constant speed in a straight line. Newton added in a straight line. And that's really, really important, and we will see this more when we talk about circular motion. So unless acted upon by an outside force. But essentially, the big chunk and the big jump in ideas for Newton's first law was actually developed by Galileo. We call it Newton's first law because Newton added to it, refined it, and made it more complete. And so that is the end of today's video. Please watch this one and then also the video on Newton's first law that will come immediately afterwards. And have a great day and see you in class.